Welcome to iLecture Online, and now that we have understood the concept of moment of inertia, let's utilize it to understand how it works with the rotational kinetic energy. And to illustrate that, here's a great example. Let's say we have a solid disk with a mass of 2 kilograms and a radius of 40 centimeters that rolls down a 25-meter high hill starting from rest. What will be its speed at the bottom of the hill, assuming no loss of energy due to friction? All right, let's imagine we have a hill, and it doesn't have to be a hill of constant steepness. It can be a hill of any kind of shape, like so. Let's say we have a wheel that starts from the top, and as it rolls down the hill, when it gets to the bottom, what is V equal to question mark? We're also told that the mass of the disk is equal to 2 kilograms and that the radius of the disk is equal to 40 centimeters. So let's first calculate the moment of inertia, or at least not necessarily calculate, but let's see what the moment of inertia of this disk is. Well, since we know that it's a solid disk, I of the solid disk is equal to the 1/2 the mass times the radius squared. All right, so we'll keep that in mind. That's the moment of inertia solid disk. And now we're going to use the energy equation to solve the problem. So we can say that energy initial equals energy final. And of course, if we want to take everything into account, we can say that any work input into the system plus any potential energy initial plus any kinetic energy initial will be equal to potential energy final plus kinetic energy final plus any heat lost due to friction. Now we can determine which of these we have and which ones we don't. Is there any work input? Well, initially we somehow got the wheel up to the top, but if we just assume that that's then resulting in some potential energy, we can assume that there's no work input into the system. Definitely there's no work input as the wheel is rolling down. Since the wheel starts from rest, it doesn't have any initial kinetic energy, so we can go ahead and assume that to be 0 as well. When the wheel gets to the bottom of the hill, it will not have any potential energy left, so there's no potential energy final, so that goes to 0. And since we were told that no energy was lost due to friction, we can say that heat loss is equal to 0 as well. So this problem simply becomes initial potential energy due to its height on top of the hill ends up being kinetic energy at the bottom of the hill. But here comes the difference. Kinetic energy can come in various ways. It can come in linear translational motion, and it can also come from rotational motion. In this case, the disk will have translational or linear motion. It will also have rotational motion. So we can now write this equation as potential energy initial will be equal to kinetic energy final linear plus kinetic energy final rotational. And let's write down what those are. So potential energy initial is simply still mgh. So the mass times acceleration of gravity times the height is what it had as the initial potential energy. Linear kinetic energy is known as 1/2 mv squared. But how do we express rotational kinetic energy? Well, it turns out there are rotational equivalents to the linear motion. Instead of m, we put in the moment of inertia I, and instead of v, we'll put in the rotational velocity omega. So this can be written as plus 1/2 moment of inertia times omega squared. And now all we have to do to complete this equation is replace I by what I is equivalent to, and omega in terms of linear motion. And if you remember, when we have a rotating disk that has radius r and is rotating at a angular velocity omega, the tangential velocity along the edge of this can be written as v is equal to r times omega, or omega can be written as v over r. So we're going to replace I by 1/2 mr squared because it's a solid disk, and we're going to replace omega by the tangential velocity over r. Remember, the tangential velocity of a rolling wheel will actually be equal to its translational velocity or linear velocity. So that will be the same as this v right here. Plugging those things in, we get mgh is equal to 1/2 mv squared plus 1/2 times I, and I is 1/2 mr squared. And then omega is v over r, and we have to square that as well. Now, simplifying this, we can see already that every term on the left and the right side has an m, so that can cancel out. This m cancels out those two m's. I can see an r squared here divided by 1 over r squared. So the r squares will disappear. This will cancel out with this r squared. And so this now becomes g times h is equal to 1/2 v squared plus 1/2 times 1/2, which is 1/4 v squared. And since we're looking for the final velocity, we have to solve this equation for v. So combining those two terms, 1/2 plus 1/4 is 3/4, so gh is equal to 3/4 v squared. Changing the equation around, we can say v squared is equal to 4/3 gh. So what I've done now is I've turned the equation around and multiply both sides by 4/3 to get rid of the 3/4 on the left side. I'll end up with a 4/3 on the right side, and then taking the square root of both sides and moving over here, I can say that velocity is equal to the square root of 4/3 gh. Now that's kind of an interesting result when you think of it. If we did not take into account the rotational kinetic energy and only assume that the potential energy translated in just the linear kinetic energy alone, then the velocity would have been equal to 2gh, or the square root, I should say, of 2gh. So now it's a little bit smaller than 2gh. It's the square root of 4/3 gh, because part of the energy is also put into the rotation of the wheel. Now, of course, plug in the rest of the numbers. We can say that velocity is equal to the square root of 4/3 times g, which is 9.8 meters per second squared, multiplied times h. We start at a height of, tells us 25 meters. And let's see what the final velocity is of this rotating wheel. So we have 25 times 9.8 times 4 divided by 3, and then take the square root. And it turns out the final velocity will be 18 meters per second. And there's the answer. So remember, when we have moment of inertia take into account, the kinetic energy that an object will have is not only its linear kinetic energy, but also its rotational kinetic energy. And the equivalent for rotational kinetic energy, instead of m, we write I, instead of v, we write omega, and then we do the replacements so we can find out what the final velocity is. And that's how you work this. All right, let's see if I can come up with some other examples of that.